let's feel like we're doing something and knock these two out. Those will go out really easy, all the chapter 5 stuff. Okay, for chapter 5, those are literally the 2 sections. And so if you see, let's say a reaction like this, I'd want to know, say, what's the oxidizing and what's the reducing agent. So what you would want to do is find the oxidation states for each item. So this one would be what? 0 and 0, -2 for this oxygen, and plus 3, yes. So this one, oxidized or reduced? Oxidized, it goes up in oxidation state. This one reduces its oxidation state, it goes downwards. But what we're interested in, especially for 5.6, is the oxidized is the one that's called the reducing agent. And what's reduced is also called the oxidizing agent. That's it. Okay? So you would say, you can either say, for example, for O2, O2 is the oxidizing agent, or you could say, if they ask for the element, you would just write oxygen. Or for iron, it would be the same either way. So it depends if they ask for the molecule or the element. If they don't state, you can put either. All right, that's it with that section. Just know the definition. Next to titrations. For titrations, typically you'll have an acid, and let's take a base. And typically we're going to be giving you, let's say this is 2 molar, let's say this is 1 molar, and this is 20 milliliters, and I want to know the volume over here. Okay? That's a typical titration problem. 3 steps. Step 1, change what you know, that one, to moles. Step 2, molar ratio to get to what you want, and then convert to the quantity asked for as the 3rd step. Okay, so those are your 3 steps. First, I'd recommend balancing the equation, writing it out. So we'd have water and potassium sulfate. In this case, we need 2 there, and I think 2 waters will do it. All right, so for the first step, let's start there. First step, you're going to take this, you're going to go 20 milliliters. I typically like to change this to liters first, so we got 1,000 milliliters on the bottom for 1 liter on the top. So now it's in liters, and now I have to multiply by the 2 molar, which is moles per liter. So that accomplishes my step 1, which is convert to moles. And the reason that happened is because milliliters are gone and liters are gone. I'm left with moles. Okay, my second step is to do a molar ratio. So I'll do that in a different color. My molar ratio would say, let's go to the one that was asked for, 2 moles of KOH for every 1 mole of sulfuric acid. Okay? So there, the moles now of KOH, of sulfuric acid, are canceling out. So now I have the moles of the one I want. So that molar ratio was my second step. My third step is to convert that to the requested unit. And I'm just going to do that through conversion. I'll use a different color even for that. So I'm going to say, I'm going to invert the 1 molar. So it's a liter on top, 1.0 moles on the bottom. That'll cancel out the moles of KOH. And I'm left with liters, which is the volume. That's what I wanted. I just made this up out of my head, so I don't have a specific answer for you. If they wanted it in milliliters, make sure to go to the next step and change milliliters. All right. That's titrations. They're pretty typical problems, and that's the reducing and oxidizing agent. Let's move on. Nice. Okay, let's see. That was chapter 5. Crush that chapter. Let's go into chapter 6. And let's do units first. So I want to tackle units. Okay, first the summary. You got to go fast because I know you need to get back and watch the Olympics. Joules is a Newton meter. Pascal is a Newton per meter squared. I will not give you this information, and typically any class wouldn't be giving this information. And a Newton is a kilogram meter per second squared. So those are the things you need to know. So for example, I gave you some random units, like let's say I gave you, and we'll go on to kind of mix this with the next topic. The root mean square velocity is 3 RT over m. That'll be an equation given on the exam. Let's work out the units for this equation just so you see how it works out. You would say, well, this would be as far as units go. 3 has no units. R would be joules per mole Kelvin. T would be Kelvin. And what would be the units of this thing on the bottom?
Kilograms per mole.
Yeah, make sure it's SI units. It's not grams per mole. It is a molar mass. It's kilograms per mole for SI units. Now let's see what cancels. The moles will cancel on the top and bottom. The kelvins will cancel in the numerator. And I'm left now with the square root of joules per kilogram. Well, let's write out joules to see what the units do. Joule is a Newton meter, and that's per kilogram. Well, now let's write out the newtons, see what that does. A newton, I'll put this in parentheses, is a kilogram meter per second squared. I've still got a meter there from before, and I've still got a kilogram in the denominator from before. Well, notice that the kilograms cancel out. What's left? It'll be equal to the square root of meter squared over second squared. Oh, that's just a meter per second, which is the unit of velocity. So that's how those units work out. And this would be a pretty typical problem for me to give you. Not just a calculation of this, but hey, here's a bunch of units, simplify them. Can you figure out what the end unit is? Okay, so that's, what happened? Yeah, this would literally be an example problem. She was asking for an example problem.
Can you actually list like numbers?
Oh yeah, that would be a different question. So you could have, she's asking about numbers. Yeah, we're going to do that in a moment. But I would ask you likely a question where I just give you the units, and you need to figure out what the end unit is as its own question. And then to be able to calculate this would be a different question. You can mix them together, but they're kind of two different things that go together. Okay, yes? Yeah, if you want to know what's given, she was just asking, somebody up there was just asking, what's given? It's in the practice exam reader. Just open it up to the first couple pages, given info, and starting on page, bottom of page 4 to page 5 is all the given info for exam 2. And it would include both R values with their units. So take a look at that before coming to the test so you know what's up. Okay, now to do a calculation, this will mix with doing the root mean square velocity. Okay, and I'm going to combo this with Graham's law too. Okay, and I'm going to combo this with, okay, this is so awesome. Look at this check mark. For those of you who like checking things off, Graham's law is going to be gone, diffusion rates is going to be gone, and where was that? Root mean square velocity. We're going to do all those right now. Okay. So, Graham's law problems can look a little bit like root mean square velocity problems, so make sure to not confuse them. The difference is a Graham's law problem will have two compounds of interest, or two gases, where a root mean square velocity is only going to focus on one gas in particular. Okay? So if you're focusing on one gas, use the root mean square velocity. If you're focusing on two gases, then go over to Graham's law. All right, so let's try this. For this kind of problem, it's pretty easy. You can even make them up yourself. You could say, pick a gas on the periodic table. So you pick radon, number 86. Okay? And then all you need to do is pick a temperature. So what's your favorite number? 7. Okay, that's a really small number, but 7 Kelvin. Okay, cool. Gas laws don't really work at this low temperature, but that's okay. So 3R is 8.3145 joules per mole Kelvin. There's R, that's a constant. T is 7 Kelvin. And then it would definitely, does anybody know why this temperature would not work? It's a fine number, it's a beautiful number. Why would this temperature not work for this problem? Okay, there's a couple, yeah, okay, so it's so cold, the particles aren't moving very much, they start being attracted to each other, so what breaks down?
Not an ideal gas.
It's not an ideal gas anymore, it starts becoming a real gas. We're breaking the kinetic theory of gas assumptions, okay? So that's why it's a funny number. Okay, so then we go to radon. It's 86. Oh, I picked the wrong number. It's 222. Now, what's wrong with the way I wrote that number right now? That's in grams per mole. I need kilograms per mole, so move the decimal point over 3 places. Kilograms per mole. And whatever that is would be the root mean square velocity. Should be a relatively small number, but that's okay. Okay, now if we had a different kind of problem, so this kind of gets into Graham's law. Let's say if I add to this another gas, let's just say H2, okay? Also at 7 Kelvin, I guess. And let's say I wanted to find the ratio of diffusion rates, okay? First of all, which one would be faster? H2 because it's lighter. Yeah, so it's lighter, it has less molar mass. And so if I want to find the ratio of diffusion rates, it usually would have to be specified in the problem, but let's say it's the root mean square velocity of radon for, that's an N, for the root mean square velocity of H2. Okay. That would just be the inverse of the molar masses, so H2 would go on top, and Rn would go on the bottom, like that. And this equation would be given. Just look at the way I write it. And then all you need to do really is plug in these numbers. The molar mass of H2, that'd be 2.016. And for this one, 222. Okay? And then you would just calculate that number. This number would be less than 1 because the velocity of radon is in the numerator. So it has to be a number less than 1. Why did I not change this to SI units?
Because it's the same units. So
They're the same units on top and bottom, so they both would cancel. You could change them to kilograms per mole, but for both of them, you'd be moving the decimal point over, so it wouldn't really matter. Yeah, what's your question, Paul? Yeah, so the question would be, what's the ratio of the diffusion rates? Because somebody asked me about diffusion rates. What's the ratio of diffusion rates of radon to hydrogen? And so I just put the velocity of radon over the velocity of H2, and then you flip, according to Graham's law, you flip the molar masses so that H2 is on top here, radon's on bottom.
So the ratio of the velocities is equal to ratio involving the masses.
That's right. That's right. She said, and this is literally Graham's law, the ratio of the velocity is equal to the inverse of the ratio of the molar masses. It's also equal to the ratio of the times, flipped, and the amounts, and the distance. It's all 4 of those. Yes?
Have you ever been asked the ratio of their different temperatures?
If they're, would you be asked about this if there are different temperatures? That wouldn't be possible to solve because temperature is not variable within Graham's law. Yeah. So you could maybe come up with a way to solve that, but it would involve Graham's law. Okay, cool. That's Graham's law, and that's where diffusion rates would come in. So if there was a diffusion rate, because it's using the word rate, they mean velocity, and so you'd be doing something like this. So that tackles all of those, actually. Let's go to the next one. Kind of related, let's do this one next, the kinetic energy. Okay? Kinetic energy. All right, there's 2 ways to calculate kinetic energy. VK squiggly, that means per mole. There's 1/2 mu squared, which really, the way we would write it is this. 1/2 molar mass, because it's per mole, times root mean square velocity squared. But I would give it to you this first way. I wouldn't give it to you the second way. Equals 3/2 RT is the second equation. Both equations will give you the identical answer. It's up to you which one to pick. Let's just do it for radon here. Let's find the kinetic energy. Well, the kinetic energy for radon, using the top formula, would be 1/2 m 222. Again, what's the problem? Yeah, this is grams per mole. I'm not taking a ratio, so I need to move the decimal point over 3 spots. I get 222 from the periodic table. And the root mean square velocity squared is what we calculated on the previous slide here in brown up at the top. Let's zoom out a little bit. So this number would go right here squared. Okay? This number right here, all that mess, go right there squared. That's one way to find the kinetic energy. I tend to prefer the bottom equation here. I think it's much easier to use. Though, again, both will give you the same answer. Another way to do this for radon would say, well, it's 3 halves R, bottom equation, 8.3145 joules per mole Kelvin, where R is a constant, times T, 7 Kelvin. And that's it. That would give you the same answer as the top equation would. But it's just easier. You don't have to worry about the molar mass. You don't have to worry about the velocity. It's just based on the temperature. What would we do different? Let's say we're using the bottom equation. What would we do different if instead of radon we said it was hydrogen?
Nothing.
Absolutely nothing. It would be an identical problem because it's based on temperature, not on anything else. Okay? So anything at 7 Kelvin, you would use this equation right here to find the average kinetic energy per mole. All right, cool? Ready to move on? All right. Got a lot to get through, so I want to make sure I get there. Let's do Daltons over water next. This is my terminology and kind of related to what you see in a question. You see a question that says something like collected over water. You see that kind of phrase, collected over water? That's a Dalton's law problem. It's just a specific type of it. It tends to be relatively easy, but the first time you see it, it just takes a little time to get used to. How the problem works is there's a reaction, and the reaction involves some gas. So gas is a product. And what they do, and you'll do this in the last lab of the quarter, that gas will go through a tube into a container with water in it. Okay? So the gas will go out of a tube, and there'll be in that container an inverted kind of cylinder that's graduated. And that'll be initially filled with water. This inverted cylinder will be filled with water, and as gas kind of bubbles out, so bubble, 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 the water level will go down. So this will all be filled with water here, and right here at the top will be the gas that's coming out of the reaction. So this is the schematic for a Dalton's law problem where gas is collected over water is what they mean. So being bubbled through water. Okay. So here's how the problem basically goes. We'll say the total pressure in this, the total pressure in the top where the gas is collecting, P total, equals 2 partial pressures. The partial pressure of the gas that you're collecting, that's the gas that's being reacted, that's coming out, and there's one more gas in that upper part of the cylinder. What is it?
Water vapor.
It's water vapor. So the water that you're collecting over also has a vapor pressure. So that's another key phrase you might see in this sort of question, water vapor or vapor pressure. That kind of indicates it's this sort of question. So partial pressure water is also part of this. Okay? Here's what happens. Typically, this here is given on a table. Let me show you what that table looks like in case you've not seen it. It's in the book. It's also in the practice exam reader. And this is what it looks like right here. Okay? So vapor pressure right there that you see. Let me zoom in a little bit. Vapor pressure, that means partial pressure of water. It happens to be in millimeters of mercury, so you have to see if that's the units you really want. You may have to convert it. And here's the temperature. So they'll give you a temperature. You just read from the table what the partial pressure of water is. Okay? So that's from a table. Usually you're looking for the pressure of a gas, and this pressure here is either given or atmospheric pressure. If it's atmospheric pressure, P atmosphere or P bar in terms of millimeters of mercury, does anybody know what that number would be? 760 millimeters of mercury. Let's say you didn't know that. Then you go back to the back page of the exam givens. This is okay, you don't have to have that number memorized. Right here where I give you the conversions, all these numbers right here, this is atmospheric pressure. So these numbers, if you wanted the number for bar, it's that number. If you wanted atmospheric pressure per pascal, it's that number. So these are the P atmosphere numbers. Okay, it's also the conversions. So that's given on the exam. So notice what happens now. If this is given or atmospheric pressure, and this is from a table, it's super easy to now solve for the pressure of the gas. It could be, that could be as simple, the simple question, or this is typically also paired, and it might say, oh, how many moles of gas are collected? If you needed the moles, you've got the pressure, you typically got the temperature, you're going to use the ideal gas law at this moment. So often in Dalton's law, when it says collected over water, we'll pair this equation with this following equation. The ideal gas law, where this would be the pressure of the gas right there. Okay? And so thus, this would be the moles of the gas. So for example, if they said, how many moles of gas are collected, they would be asking for this number right there. Pressure of the gas, you get from the equation up above. Volume, that's given. R is a constant. And T is given. So if whoever asked this, it's typically these two equations. Use the first equation first, top equation first, find for the pressure of the gas. Then use the second equation and solve for what they asked for. Typically, it's going to be the moles of the gas. And everything else is given. Yes?
For the pressure equation, you have to put it in millimeters of mercury.
For this equation, you would just use, if she's asked about the units, you would just use the units that are given. So for example, on the table, this will be given in millimeters of mercury. So I use this in millimeters of mercury to solve for this one. But, anybody, what units am I using down here for pressure? Atmosphere. So I need to do some conversions, and that's pretty normal on this kind of problem. Okay? All right, that also gets me into the ideal gas law question that somebody else asked, so let me do that now. Remember, when you're doing the ideal gas law, often you're just going to use this equation. However, it can be paired with other equations as well, like density and molar mass, which is mass of moles. So I forgot what equations of those I give you. I definitely give you the ideal gas law. Let me see if I give you anything else. As far as, no, I don't think I give you anything else. So you have to know the equation for density. You have to know the equation for molar mass. I don't see it here in any of the givens. Okay? So these two you'd have to know. You have to know molar mass is mass over moles, density is mass over volume. Okay, so it could be that you're asked to do some sort of conversion. Like on a previous test, I think I said, at a given temperature, what's the density of neon? That's this kind of question, where it's one compound. I say something like density, and everything else is given. Okay? So if you need to do some sort of substitution, make sure you can do that. So as an illustration, let me just do a little bit. You need to do a substitution to say put these equations, kind of put these two together. For me, the easiest way is to say, well, pressure is moles over volume RT. Moles over volume kind of gave me towards density, so that's why I start there. And then I'll also, using this equation up there, I'll say, well, moles is mass, lowercase m, over uppercase m, molar mass. Just doing a little cross multiplication. So I can substitute that in, these two together. Let's go to the next page. So pressure is moles, mass over molar mass, over volume, RT, which is just a little simplification, mass over molar mass, volume, RT. Okay? And then I can kind of simplify however I feel like it. But you might notice that I have this right here, this mass over volume, that's density. So that's really easy. Another simplification, if I wanted to get density in there as well, RT. And so now I have pressure equals density divided by mRT. That's an easy variation. So if you see a question where they're focused on one particular gas, and a lot of information is given, maybe you know the temperature, or it's an STP, something like that, and then they ask something funny like, what's the molar mass, or what's the mass, or what's the density, they're talking about this sort of question, okay? So if you see the keywords, like you have a single gas, there's words like density, molar mass, or mass, and you know, say the temperature and the pressure, it's this sort of question. Alright, that's all I got for that one. And I think I'm moving away from chapter 6 into let's do chapter 8, because that'll be an easy win. Radii. Okay? A typical question for radii that you'll see in the next lecture that I'll do. Basically what you need to know, if you look at the periodic table, and you might want to write this on your exam once you open it up, is as you go to the left and down on the periodic table, you're increasing the radius. Okay? And that's basically because of the screening effect. Okay? So to the left and down on the periodic table is increasing the radius. And if you want to see a little summary of this, I'll point to this in our next lecture. But page 80 of our reader has a summary of all. Basically, this is the summary of chapter 8. This one picture right here. So radius and screening go to the left and down. As you go that way, they increase. Z effective increases the other direction. And there's a couple other variables here we haven't learned yet, but they're in chapter 8. Okay? So that's all you need to know. So given for the radii, if I give you any two like sulfur and strontium, and I say which one's bigger, you just say, well, to get from sulfur to strontium, I go to the left and down, so strontium has to be larger. And that's it. I could not ask you a question to compare these two. You can't be asked those two because they go along the wrong diagonal. Okay, it's not left and down. So this kind of questions comparing these two kind of elements could not happen. Okay, just if you're curious about that. Now also notice that if you have an anion, so if I had sulfur 2 minus, any anion is significantly larger than their counterparts. So this is much, much larger. Okay, I'll use two muches there. Much, much larger than sulfur, but it'd also be larger than pretty much anything on its row. So it's so big, it'd be larger than neutral chlorine, larger than neutral phosphorus, larger than neutral silicon. It's larger than pretty much any neutral next to it. In contrast, if you look at a cation, so let's say aluminum 3+, there's a cation for you. These are really, really small. Okay? So aluminum 3+ is really, really small. It's smaller than anything on its row. Neutral silicon, neutral phosphorus, neutral magnesium, neutral sodium. It's really, really small, significantly smaller. So if you see a cation in a list of things to pick from, assume that one's immediately the smallest. If you see an anion in a list, immediately think that's the biggest. And then sort from there. Yeah?
So for your example of oxygen and chlorine,
Yeah.
would chlorine be an energy level difference though? Like,
Chlorine would be an energy level down.
yeah,
So that you would think bigger, because you're going down the periodic table, but it's also to the right. So you're mixing two trends. The right makes it smaller. And in this class, we're not dealing with that, going along that diagonal. So you won't have to worry about it all. And sometimes there's trends. Usually, you're right. As you go down, it gets bigger, but we're not going to worry about that. Okay, anything else with radii? So it's literally just looking at the periodic table, remembering Cations are small, anions are really big. Yes?
So anything that's diagonal of each other that we can't compare, right?
Along this diagonal going this way. So she's asking about the diagonal. You can compare fluorine and sulfur. Sulfur is definitely bigger than fluorine. But oxygen and chlorine you can't really compare. Or nitrogen and sulfur you couldn't compare. But you could compare nitrogen and silicon. Silicon is definitely larger. Does that make sense? So it has to be along a diagonal that goes from the upper right to the lower left. That kind of diagonal. Oh, what's that? I couldn't tell which way your fingers went, but maybe she had a lot of finger movement in that last action. But later, if it's still confusing, you can draw it out for me and bring it up. Okay, cool. But definitely don't make this stuff more complicated than it is. It should feel pretty easy once you get used to it. Okay, let's go back. Here we go. Okay, chapter 7. Here we go. This chapter should be easy. I know it doesn't feel that way when you first learn it. Okay, let's do the uncertainty principle first. Okay, for the uncertainty principle, here's the equation you'll be given. What does this mean? The change, the delta, means uncertainty in position times uncertainty in the momentum is greater than or equal to h, Planck's constant, over 4 pi. Because that's kind of a funny way to look at it, I usually rewrite it like this. X times momentum is just mass times velocity. And then the uncertainty, one way they toss that in is giving you a percentage in the problem. So if you see keywords like precision, accuracy, uncertainty, anything like that, it's one of these problems. And then it's just easy enough to make this equal sign equals h over 4 pi. All right, and so what is going to happen is I'll underline these two, this one and this one. Of the two I just underlined, one of those is given, the other is an unknown. Okay, for a pretty standard problem. Everything else is known, so you'll know the mass, you'll know what percentage it's given in the question. H and 4 and pi are all numbers, so you know all those. So it's just between x, the position or length, and u, the velocity. So what they'll say, and so it's plug and chug, okay, that's it, use SI units. So it'll say something like, you know the position within, 1 nanometer and accuracy of 2%, something like that. Okay, you know the position within that distance, and they'll want to know what's the velocity. Okay, that would be a typical kind of question. And you can say, let's say this is for electrons. Okay? So what you would do is say, okay, you want the velocity, so velocity is h over 4 pi mx%. Okay? Let's go to the next page. That would be h, 6.626, this is given on the exam, times 10 to the minus 34 joule seconds. 4 pi, those are just numbers. M, for the electron that's given on the back of the exam, it's 9.109 times 10 to the minus 31 kilograms. X, given in the problem, I said it's 1 nanometer, you should put that in meters. That would be 10 to the minus 9 meters. Okay, nanometers into meters. And then the percent, that's 2% given in the question. Just make sure to change that to a fraction, okay? So we're using SI units, putting everything in, plug and chug, that's it. And that's it. You just put that in your calculator. Whatever that is, that's your answer. Yeah? M is the mass, and in this case I said it was electron. This is the mass of electron, it's on the back of the exam. If it was something, I think on the back of the exam I give you a proton, neutron, electron mass. Something not that, I'd have to tell it to you. Yeah, because you wouldn't. It's not something we would ask you to solve for. It would have to be in the question if it's not on the back of the exam. Okay, so that's uncertainty principle. Okay, let's move on. Next, let's do Let's do wavelength. Wavelength. Wow. Somebody's squeaky voice up there. Okay. Wavelength. What are the equations for wavelength? There's the de Broglie wavelength, h over mu. That's one equation for wavelength. You know you're going to use this one. This is SI units only. You'll know you'll use this one if you're concerned about one item. Usually it's an electron or something small, but it doesn't have to be. And they either give you velocity and ask for wavelength or vice versa. So the two ones that we're worried about are this and this. Those are your main variables. Velocity and wavelength. You know it's a de Broglie problem for sure. You also, this will mix with another question. You also have wavelength in the particle in the box. I think it's 2L over n. And we'll do this in a little bit. So, but that goes with the particle in the box. Where else do we see wavelength? You also see wavelength in this equation, hc over lambda, which is from c equals lambda nu. And this can also be equal to the Rydberg constant, 1 over n initial squared minus 1 over n final squared. So you see it in that energy equation or the speed of light equation. Am I thinking of another wavelength equation I'm missing? I think that's all you learned in this chapter. I believe that's it. So you see something about wavelength. It's got to be one of these equations. Just by process of elimination, if you look at the variables given in the question, right, without knowing anything, you can pick the right equation. Okay? And these are all the chapter 7 equations are plug-in sort of equations. So that's wavelength. Let me, since I kind of introduced it, I'll take this one, this equation right here, and go into the next topic, which somebody asked me about, which is the particle in a box. Particle in a box. We really didn't spend much time on this, so there's just a little bit that you know. This was a two-dimensional look at how an electron behaves if it behaved in a plane. So what you saw is a particle in a box. They have an equation to describe an electron, and the electron's sinusoidal, or it makes waves, a standing wave. And so we describe it with a wave function that we call psi of x. And you can plot this, psi of x versus x, and we say the length, and we just call it a box. It's a y-axis, an x-axis, and another side just to make it look boxy. And it goes from 0 to the length of the box L, capital L. Okay? And then there's all kinds of functions you can put in here. So for example, here's one energy right here. So I want you to be able to tell me some pretty typical things. First of all, how many nodes do you see here? You should see 2 nodes. Right, one right here and one right here. That's 2 nodes. Okay, now this, the one node happens at, what's the first node? X equals L over 3. You see how it's split in thirds? There's 3 pieces, 1, 2, 3. So it's L over 3. The second one is 2L over 3. 2/3 the way over. The first one's 1/3 the way over. Second one's 2/3 the way over. 2 nodes. What else do you know? What's n? 3. Yeah, nodes is 1 less than n, so n is 3. That ends up ultimately being our principal quantum number, but here it's the orbit or energy level number. So as n increases, the energy increases. That's basically all you have to know. Oh, yeah, you can find the wavelength. So that's 2L over n. I know n is 3, so it's 2L over the number 3. What does that mean? That means you have one wavelength as you go 2/3 the way down L. So 2/3 of L is one wavelength, which is what you can see. One wavelength there, that's about exactly 2/3 of L. One other thing we could do, so we would draw the graph for you, you just need to interpret it if you needed a graph. One other thing we did when we did that topic is talk about psi squared. Psi squared represents the probability density, or where you are most likely to find an electron. For that last one, I'll draw this out for you. So this is for the last picture. Let me draw it for you. It would look like this. This would be size squared. These humps are all of equal height versus x. And if I gave this question, all you'd have to do is label the graph. And most likely I'd ask you where you're most likely to find an electron and put an asterisk at that point. So if I asked you that, you would say, oh, well, let me ask you. Tell me to stop when you see, I'll trace the curve. Tell me to stop when you see the highest probability of finding an electron. Yeah, here. Okay, so wouldn't be here. This is where the node would be here, and then there. Okay, so it's to the top of the curves. Yeah?
Could you give us that diagram as well, or do you know how to get that?
Again, the diagrams I would give you. Yeah, that's what she was asking. Definitely give you the diagrams. You just have to label it, find the nodes, find the ends, stuff like that. L is just the end of the box. The box goes from 0 to L, it's a variable.
Question?
Just a second, I'm working on L here, and then I'll get to your question. It's just the length of the box. So 5 meters, a foot. It's totally unnecessary to know L. We're usually going to be doing that as a variable that we don't have to plug in. Yeah, there was another question? Yes?
Do you need to know how to calculate like the value of the asterisk on the x-axis?
Do we need to be able to find where the asterisk is in terms of L? Usually not, but it would just be halfway. So it would be a sixth of L in that case. Okay, let's go on to the next one. This was a bigger topic for us. And we'll just do them. Oh, you said particle in the box. Quantum numbers, orbitals, electron configurations. And that'll kind of end us out here. What would be most helpful? Just examples? Yes?
Yeah.
Okay, examples. So let's start with quantum numbers. There's a couple different types of quantum number questions. Okay? So let's try a couple. First, one type of question would be like, let's say I give you 3d m sub L equals -3. Okay? And I would ask you, is this allowable or not? So what you need to do, I need to know, is this a possible set of quantum numbers? You'd say, well, n equals what? 3, the first number right there. L equals d, which is the number 2. So if L is 2, could m sub L be -3? No. If L is 2, m sub L is between -2 and +2. So this is not possible. That number is too negative. If -2 would work, or -1, or 0, but that's not possible. That's one type of question. Another type of question would say, well, n equals 2. And I would say, write all the possible quantum numbers that go with n, and the key word would be possible. So for n equals 2, all the possible quantum numbers would be, well, what could L be? 0 or 1. If L is 0, m sub L would be 0. Yeah. If L is 1, m sub L would be 0 plus 1 or minus 1. What would m sub S be? Just plus or minus 1/2. It's not. M sub S is the one quantum number, the spin number, that's not connected to the other 3. There's 4 quantum numbers you need to know about. So yeah. Yeah, that's exactly where I was going. Add up the total number of electrons for the m sub S. Is that right? Okay, yeah. So another type of question would be, how many, for n equals 2, if you're given this number, how many electrons can go into that energy level? So in order to count that, basically it's based on the number of m sub L values that go with, in this case, n equals 2. So how many total m sub L values have I written down so far? Well, I've written 3 here, and 1 more here, a total of 4. Is that okay? So each m sub L value holds how many electrons? 2. So if I have 4 m sub L values, that's a total of 8 electrons could be in here. Okay? So a total of 8 possible electrons. Should be able to do that for any value of n we give you. So the bigger n gets, the harder the calculation gets.
So 0 counts twice.
0 counts twice, yes. Is what somebody's asking, because this is a 2s orbital, which is different than a 2p orbital. Okay? Okay, another type of question you could be asked for quantum numbers is, let's say we said you have 1s, let's write electron configuration, 2s2. Yeah, that's good. And let's say I wrote that out. So in this kind of notation, 2s, 1s2, 2s2. Okay? For example. So I wrote that out for you. And then I indicated a particular electron. Which one do you want to do? Electron number 1, 2, 3, or 4? 3. Okay, that's the first number I heard. Let's focus on that electron right there. Okay, I want to know all 4 quantum numbers right now. What's n? Have to be the number 2 because it's in a 2s orbital. What's L?
1.
It's not 1.
0.
It has to be 0 because it's in an s orbital. Okay, what's m sub L? Has to be 0 because L is 0. What's m sub s?
Plus 1/2.
+1/2. How did you know that? Because it's an up arrow. Okay, so I can just have a picture, point to an electron, and have you tell me all the 4 quantum numbers for a particular electron. Okay, those are the common these kinds of questions. Now let's move on to the orbitals, because they're related. Orbitals, I want you to draw the orbitals. Would it be, oh yeah. M sub s is a spin quantum number. +1/2 means an up arrow. -1/2 means a down arrow. Yeah, she's asking, is it always going to be one or the other? Yes. Up or down, that's your only 2 choices. Okay. Yes. This? This? No, you don't. I didn't have to add anything. I don't know. To add what? Oh, I can't think of a possible question where that would be, unless you find one with the show me, but I can't think of one. Okay, yes, one more that I'm going to go on. Why is there 8 possible electrons? Because, yeah, for n equals 2, I was asking how many possible electrons could there be? Well, L is 0 or 1. The 0 has an m sub L 0, and the 1 has 3 values. Each one of these orbitals, and there's 4, for the 2s there's 1, for the 2p there's 3. Well, 4. Each one can hold 2 electrons, so that's 4 times 2 is 8. So you would, if you wanted to practice, you can do this for n equals 3, count the number of electrons. I think on a final one time we had n equals 6. It's going to start getting really big pretty fast. But you should be able, any n within reason, should be able to count the number of electrons that could be there. Okay, if that didn't make sense, come see me afterwards. All right, now I don't know what I was doing orbitals, yes, orbitals. Okay, there's like I'm expecting to be able to draw the S, the P's, and the D's. Should I draw that out, or should I just do like harder examples? Okay, we'll do harders, I assume, or harder ones. I'll assume you know how to do the easier ones from just looking at lecture notes. Okay, so let's say I had you draw a 4pz orbital. So what would that be? Well, that would be a pz orbital. So you write on the z-axis, so this pz. How many nodes am I expecting, by the way? Yeah, 4 minus 1, n minus 1, or 3. How many would be angular? There's one angular node, it's right here. This is a node, splitting the middle. This is called an angular node. It's a planar. When it's planar, it's called an angular. Every p orbital has at least, has only one and only one angular node. Okay, the other two nodes are called what? Radial, and where are they? Yeah, they're kind of like circumscribed circles in the p orbital. Here's one. So this is a node, and this is radial. I'll put RAD for radial. And then there's a second one, and both of those lines on top and bottom are for this other node. This is also radial. So there's two radial nodes. You know it's radial when it looks like a circle. And then there's one angular node. Again, that one's flat. It's planar. So a question would be just like draw it, label all the nodes. Let's do one more. Let's do a 4D x squared minus y squared.
Question.
Yeah.
Do you have to shade it in?
Oh, do you have to do the shading? If you do it, that's totally fine. But for this exam, we won't grade you down on it. The final though, it's important. And if you're curious on the shading, you just have to flip the shading like this. Okay? But on the final, that's important. Right now, it's not a big deal at this point. Okay? So don't worry about it now. If you don't know it, it's okay. All right, 4dx squared minus y squared. How would you draw that? Well, draw a dx squared minus y squared. And that's a clover leaf, four-leaf clover on the x and y axis. Okay? And then, how many angular nodes does this have? It has two. It will have two and only two, and they're planar. One's there, and one's here. So this and this are the angular nodes, and that's two. How many more? What's the total nodes, by the way?
3.
Yeah, 4 minus 1, just like above, or 3. So there's one more node. Again, that's the radial node. There's one node left. It's the radial node. And it'll look like this. It'll be a circumscribed circle going through all 4 lobes of the clover leaf. And this is the radial node. Okay. These would be pretty tough drawings as far as I'd be concerned. Be a tougher question if I asked you this. A more normal question would be like, draw all 2p orbitals, or draw all 5 3D orbitals, something like that. Be a more like middle of the road question. Okay. That was the orbitals. Let me think if there's any other questions I could ask you in the orbitals. I'm trying to remember.
Yeah.
There probably is, but I can't think of them at this moment. Well, that's good. We finished our whole list. For those of you who like checking lists off, we've checked all our lists. What we're going to do now is I'll dismiss all of you who are bored and need to go watch MTV. Those of you who want to stay, just move on closer to the front and I'll answer specific questions from you. So I'll give you a minute, whoever wants to go can, and we'll resume in just a minute.